In this video, we're going to talk about percentage yields and atom economy. We're going to talk about what the definitions are for each and the equations that you use to calculate them, and then go over some exam-style questions. Atom economy is the proportion of desired products compared with the product's form done through an equation. So the equation is percentage atom economy, looking at the total molecular masses of all the desired product, and then divided by the total molecular mass of all the products, times by 100. So why do we even do this in the first place? Why do we have atom economy as a calculation? Well, it's because there are certain benefits we get from having a high atom economy. We want a high atom economy because it reduces the amount of waste. If you have a reaction and you have 4 or 5 different products and you only want one of those, that means the rest is waste, and that will go into processing plants or landfill and take lots of energy and resources to get rid of or make safe. Okay, so we want to reduce the amount of waste we have first and foremost. If you look at atom economy, it gives society a desire to find a use for all the products so that you don't have any waste. So that innovates and makes people think, well, what can I actually use this for that's useful? Okay, and one example of that is if you have the Haber process, which is a reversible reaction, any unreacted reactants are recycled and reused inside the whole process. So it's very important that you find a use for all the products, or essentially in that case for the unreacted reactants. It also increases the desire to find environmentally friendly ways of disposal, and some questions in exams can base their thoughts on this. So for example, if you have a reaction that has an acid as a product, and it might say, what's an environmentally friendly way of disposing of that? Well, an acid will react with a base to make a salt plus water, which is far less harmful than the acid itself. And so that's a very, very common question. So let's talk about the different types of reactions that can give different types of atom economy. So this is propantuol, and you can dehydrate it and turn it into an alkene. Now, I'm not too worried if you haven't done these reactions before. The process is more important to find out is how many reactants and how many products we have. So we have this one reactant here, and then we have 2 products, which means we're eliminating the water. The desired product is going to be the alkene. Well, that means we must have some waste. And because we've got some waste, we're going to say that this is less than 100%. Because the atom economy is the molecular mass of the desired product divided by the molecular masses of all the products. Well, if we have a waste product, that means we're definitely going to get less than 100%. And whenever you remove something from a molecule, we call that reaction elimination. So it's eliminating water here. The next one is substitution. Now, substitution in this case is when you have 2-chloropropane reacting with hydroxide. It's also called hydrolysis. Okay, and the OH- substitutes out the Cl. So the Cl, essentially in this one, the Cl is our waste product. So this is our waste product. So therefore, that substitution, because the OH is substituting for the Cl, it's got to be less than 100% because you're making a waste product. The real one I want you to look at is this one, which is an addition reaction. It has 2 reactants turning into, and here's the conditions, turning into 1 product. So both reactants are being used up to make 1 product. Therefore, the total MR of the desired product is divided by the total MR of the desired product, because there is only 1 product. Okay, so it's 100% atom economy. And if we could do all reactions like that, it would be great, but we can't. So the desire is just to make the percentage atom economy as high as possible. Now the questions. We'll get a common question here, but before I do that, I want to show you the exam tip. So the exam tip is as follows. If we're doing these calculations, you have to include the balanced equation and use the balancing in the equation. Okay, so if you've got 2 moles of a product, you have to times that number, the molecular mass, by 2, for example, but we will do that in our examples. And recognise addition reactions to save yourself time in the exam, because if you see an addition reaction, you know straight away it's 100%, and that can really help you in terms of multiple choice questions. So here's an example of calculating the atom economy for the preparation of PCl5. Now PCl5, without even knowing anything about it, it's 2 reactants going into 1, so it's 2 things adding together. So essentially it's a kind of addition reaction. Okay, and therefore must be 100% straight away. So without much thought, I can just say 100% and move on to my next question, if that is the case. Now let's look at a calculation. So the calculation we're going to do, we're going to use that equation again, okay, and we're going to calculate the atom economy for the preparation of butanol. Okay, and we've been given this in molecular formula for now. Okay, but here is the balanced equation. And we can see straight away that the OH is substituting out the Br, so this is definitely going to be less than 100%. If I give you the molecular masses and the atomic mass in terms of the Br minus, you can see we've got the details we need to do the equation. So let's move that over to the other side and bring that equation in the middle. So if we want to work out our percentage atom economy, all we do is say, okay, here is our, and I'm going to shorten it to percentage AE, just to save space, atom economy. Okay, and then the total MR of our desired product. So our desired product is the butanol, so we know that the butanol is 74. So it's 74 grams per mole. Okay, and then we're going to divide that by 74 grams per mole plus, because we have the Br minus as well, so it's going to be plus 79.9. Okay, let's just do that out there. Okay, and then we're going to finish it off, times that by 100. Okay, so we have got our percentage atom economy, the molecular mass of our desired product divided by all of our products, which then equals 48.08%. Really important here is that you do it to 2 dp. They expect it every single time to 2 dp if you are doing a percentage. And that is how you do an atom economy question for the production of butanol. We're now going to do a question that uses the balancing in the equation. So calculate the atom economy for the preparation of methane, CH4, and we've got an equation here about producing methane. Notice that you have another product, which is water, which we'll need to include in our calculation. Also, there is a 2 by it. We need to include that 2 when we're doing the calculation. We need our molecular masses, which are there on the right-hand side, and let's put it all to the right, and then highlight the main parts as we normally do in these videos. So you've got highlighted parts here, your 2 really important, and your molecular masses. So what we have to do is do percentage atom economy, as we've done before. Okay, that percentage atom economy, our product is methane. We look down at our molecular mass of methane, we know it's 16, so 16 grams per mole. That's our only product, okay? And then we do all of our products. Okay, so basically that means to add to our, so we've done our methane, we now need to do our water. So that's our desired product divided by our total products. Okay, and that is where people normally make a mistake. They either forget to put the 100 on, or they forget to include the balancing. So let's include the balancing. We know there are 2 moles of water, so let's do 2 times that. And then there we go. So there is our equation for working out the atom economy. Okay, and all we now need to do is do it to the 2 dp that we're used to. So that is 30.77%, and that is 2 dp. Basically, that is how you do an atom economy question when the balancing in the equation is not one-to-one. You need to use the numbers, essentially, inside your calculation. We're now going to talk about improving atom economy. Now, you can do this by using elements with a lower atomic mass. That changes the molecular mass of the molecule as well. But it's typically done if you have a metal in group 1 or group 2. So let's look at an example of that. So if we have an alcohol that has been turned into a haloalkane, and you see this is the product we want here. Notice that we're doing this with KBr, and this K here ends up in our waste materials over here. So this is all waste. Okay. Now you use the molecular mass of these products. Okay. So if you took the potassium here, which comes from here, and you replaced it with something with a lower atomic mass, that can change the overall atom economy. So let's look at the atom economy for this reaction. If I was you, I would stop this video right now and I'd calculate it yourself to give yourself practice, but it is 33.04%. So if we do what I said and we do the same reaction, we try and improve the atom economy, make it higher, okay, if we change the potassium here for a similar group 1 metal, which is sodium, if we just change that for a sodium, that means the molecular mass of these products will be lower as a result, which means if you're using the calculation for percentage atom economy, means that you'll get an increased atom economy of 37.22. And I'd encourage you to put these into a calculator yourself and do it yourself, and you'll see the difference. We're now going to move on to percentage yield. And you may have used percentage yield in GCSE by using masses, but when you're doing A-levels, you use moles. So it's actual moles of your product divided by the theoretical moles of your product. And all the questions in A-levels are based upon this calculation. To do that calculation, you'll need to use moles equals mass over molecular mass, and you'll need to rearrange it so that mass equals moles times MR. So this is the same equation, just rearranged. And you'll need to use a variety of these throughout the 3 questions we're going to cover. So first of all, we've got propan-2-ol reacting to form 2-bromopropane. Okay, so we're given a mass of propan-2-ol and a mass of our 2-bromopropane. And so what we have to do is work out our actual moles of product, and we can do that from the moles of the bromopropane. And what we need to also do is do the theoretical moles of the product. Now that can come from the mass of the reactant. So we've got a mass of reactant here. If we turn that into moles, and that will give us the number of moles of propan-2-ol, which will then give us the number of moles that we should have made of 2-bromopropane, because there's a 1-to-1 ratio. So if I have 1 mole of this, I will make 1 mole of this if it is 100% yield. So let's actually do the question. So we have to use our 2 equations. We've got moles equals mass over molecular mass. And we have to work out the percentage yield. So we have to work out the number of moles of our product and the theoretical moles of the product. We're going to start off with the number of moles of our propan-2-ol. So propan-2-ol is our reactant, and we can get our theoretical moles of product from that. So what we've done is taken the mass from the question, 24.0, divided it by the molecular mass of propan-2-ol, and we have 0.4 moles of propan-2-ol. But that equals the theoretical moles of the product, because there is a 1-to-1 ratio here. So this is really the number of moles of the 2-bromopropane that I should make. We then have to do the actual moles of our product that we make. And there is our 2-bromopropane there. We've got our mass of the bromopropane divided by a molecular mass of the bromopropane equal our number of moles. So this is our number of moles of our product, and this is our theoretical moles of product. We now put them into the equation down the bottom. And you can see I've done exactly what I said, put the number for the actual divided by the theoretical. And the important thing here is calculator. So This number here has 3 dots by it, which means that it's in the calculator, and I've kept it in the calculator. I've not rounded. You don't round any numbers until you get to the final answer when it comes to your A-levels. So that ends up in 0.114 divided by 0.4 times 100 equals 28.74%. We're now going to go on to progressively harder questions. So here we have 6 tonnes of NO2, which was produced in step 1. So this is our NO2 here, and it is produced in step 1 and completely used up in step 2. That means whatever you made in step 1 is whatever you start with in step 2. So we had 6 tonnes of the NO2 in step 1, so that means we started with 6 tonnes in step 2. We've made 3.15 tonnes of the nitric acid, which is there. Okay, and now we need to move on to calculate our percentage yield. Now the important thing is though, it is in tonnes. And we'll talk about what that means for your calculation next. So we've highlighted the important parts, the 6 tonnes, the 3.15 tonnes, and we've highlighted the balancing in the equation. You can see there's a 3 and a 2. That means you make 2/3 as much HNO3 as you have of NO2. So if you made 3 moles of NO2, you would make 2 moles of HNO3. And you need to take the balancing into account in this question. So first of all though, it's a number of moles equals mass over molecular mass again. But we've got tonnes. So our tip here is to go to your data sheet and look for the conversion for tonnes, which is 1 tonne equals 1 times 10 to the 6 grams. And remember, you can use a times 10 to the X button or an EXP button on your calculator to do that as well. So we do the first calculation, which is our actual number of moles of HNO3. We know we made 3.15 tonnes. That's converted into grams, 3,150,000 grams, divided by the molecular mass of the HNO3, which means 50,000 moles. We then go for the theoretical number of moles. Notice we've shortened this a little bit and it just says theoretical number of moles of HNO3. Now to find out the theoretical moles of HNO3, we need to use the moles of NO2. So what we do is we take the moles of NO2, the mass, of NO2, and we divide that by the molecular mass of NO2. So this is our NO2 molecular mass and our NO2 mass here. That would give us our number of moles of NO2, but we want to convert it into our theoretical moles of HNO3. And we have to do that via the balanced equation, which has 3 moles of NO2 will give 2 moles of HNO3. So we can times it by 2/3, and that will give you the number of moles of HNO3 you should make. You can also divide this number by 3 and times by 2 in your calculator as well. There's 2 ways of doing it. We then put our numbers in, our 50,000 and our 86,956, and we put them into our percentage yield calculation. And we have 50,000 moles divided by 86,956 times 100, which is 57.5%. The last question we're going to do is probably the most common one in exams, and I would recommend that you practice doing it on a regular basis. The chemist prepares 2-chlorophenol from phenol, and you can see here is our phenol, and here's our 2-chlorophenol right here. We've made 2.57 grams of this 2-chlorophenol, and there's 93% yield. Now, to do this question, we're going to have to use slightly different versions of our equations. And we're also going to have to give it to an appropriate number of significant figures. So our exam tip here is give it to the lowest number of significant figures given in the data. So if it ever says give to an appropriate number of significant figures, give it to the lowest number of significant figures given in the data. And if you see here, the lowest is 3, which is here. So I'm going to give my answer to 3 significant figures. Also, as I said, we're going to need to use a slightly different use of these equations above. So if you look at the change on my right-hand side here, you'll see I've just changed my theoretical moles of my product. And what I'm going to say is if I have actual moles of my product, which I can work out actual moles here from the mass, and I divide it by my percentage yield, 9302, and then times by 100. What I'm doing is turning that number of moles into what would be 100% yield number of moles, and would essentially be my theoretical moles of product. We also have our moles equals mass over molecular mass, which can be rearranged into mass equals moles times MR. And the question asks you to give the mass, so we need to rearrange that equation to give the mass. So if we put this over onto the right, so we can answer the question, and we've highlighted all the main points, 2.57 and 93.02. And also we've shown there's a 1-to-1 ratio of the phenol with the chlorophenol. So you can see there's 1-to-1. So let's look at the first part. What can we work out? We can work out the mass of the chlorophenol. So and we can use that to work out the number of moles. So here's the number of moles. We've got 2.57 grams, which is over there, and we have 1.28.5 grams per mole as the molecular mass, which we've worked out. That's 0.02 moles. So if we put that into this equation, say 0.02 moles divided by 93.02 times by 100 would give our 100% yield here. And again, we put our 3 dots because it's a very long number and we're just going to keep it in our calculator. Now, because it's a 1-to-1 ratio, that will be the number of moles of our phenol. So 100% yield of this would be 2.15 times 10 to the minus 2, but that would be 100%. That would be 100% converted into the mass of, or the moles, sorry, of phenol. So that is now our moles of phenol, and all we have to do is put our moles in there times by the molecular mass of phenol, and we'll get the mass of phenol which we started off with in the first place. 2.15 times 10 to the minus 2 times 94 equals 2.02. Notice I go back to 3 significant figures because I'm using an appropriate number of significant figures, as in the lowest number of significant figures that are given in the question. And this is the most common question you will do in your A-levels when it comes to percentage yield. So practice this and make sure you're good at it.